So hello everyone and welcome to this webinar called Production Line Testing of Audio Devices. My name is Santiago Raches. Today I will be presenting together with my colleague James Kelly. We are both part of the Axiometrics Global Technical Support Team representing specifically the brands Audio Precision and Grass Sound and Vibration, two of the three brands of the Axiometrics Solutions Group. Just so you know, this webinar is going to be recorded, so you will be receiving a copy of this recording in a couple of days from now. Another important thing to know is that you're all muted, but if you would like to leave a question or to ask a question, you can go to the dashboard of this GoToWebinar platform, and there's a section called questions where you can write them over there. We will be answering them during the presentation, and if there's any time left by the end of the webinar, we'll continue answering the questions there. If you stick till the end of this webinar, when we finish the broadcasting, you will be redirected to a website where you can leave us some feedback. But otherwise, you can use the following emails: support@grassacoustics.com or techsupport@ap.com, where you can ask any question after the webinar. And finally, also in the dashboard section of the GoToWebinar platform, you will find the handouts section where you can download a PDF copy of the presentation, and you will also find all the important links that you will see in the different slides of the presentation with more information about the products we are mentioning today. So without further ado, let's look at the agenda for today. I'll give a short introduction of the webinar. We'll talk about the different challenges that you can find in a production line environment while testing audio devices. We will particularly discuss acoustic test chambers, specifically the Grass AL30. Then we'll talk about the brand new production line microphone from Grass, the 40PM, that has the EQ set technology. I will talk about the specifics of this technology and why is it a game changer. And then my colleague James Kelly will be talking about some audio precision products for production line testing of audio devices, particularly the APX 517 and the APX 500 Flex interface. I will finish the webinar with a system demonstration with all the elements that are mentioned in this webinar today. And last but not least, we'll have the Q&A section. So if we talk about AP and Grass, they can be considered as trusted advisors when it comes to audio devices testing. Grass particularly has more than 25 years of experience supplying not only measurement microphones, but also acoustic test fixtures. And AP has more than 35 years of supplying state-of-the-art analyzers and also software for acoustic and audio testing. Particularly, I could say that the audio industry has experienced a very big change and a lot of evolution in the last 2 decades, and both Grass and Audio Precision, as part of the Axiometrics Solutions Group, have been involved in every step of this change by designing equipment to fulfill our customer needs. Here in the slides, you can see some of the brands that have been with us along the way as customers, but also providing valuable feedback to us. Now let's talk about the challenges that we can find in a production line environment. First of all, let's talk about efficiency. This is a very common topic because in a production line environment, we would like to test as much equipment as possible in the least amount of time. But we also would like to get very reliable results from our testing. And this is typically that we need to find a balance between these two topics, between efficiency and reliability. Particularly with acoustical testing, we find the situation where if we reduce the test time too much, we might get unreliable results out of our testing. So we might need to increase the time in testing each device in order to get reliable results. So it's usually a trade-off or a balance between these two elements. We would also like to have easy to operate equipment. We wouldn't like to use too much time in order to train our operators in how to properly use the equipment, how to get reliable and repeatable results with the test equipment. And that's why we would like to reduce the complexity of our test setup as much as possible. Another typical challenge, and goes particularly for acoustical testing, is a background noise. You know, we are in a production line environment. We have a lot of people, a lot of machinery, and this will create a lot of noise. And we wouldn't like that noise to interfere with our testing because that will degrade the quality of our results. And it will require us to repeat the test again. So this is something we need to tackle and we need to reduce as much as possible. But not only the background noise, we also have the test noise, and that's the noise that is generated by the test itself. We might have a loudspeaker producing a reference signal, and that will disturb the environment. It might disturb the operators around the test bench, or it might disturb the test that is being performed in another test bench. So we need to tackle this issue as well. Of course, we can't forget about the cost of operation. Every hour that we have a production line running, it costs us money. But also every hour that our production line is not running because of downtime, because of calibration, because of broken microphones or unreliable equipment, that also costs us money, and we would like to reduce the downtime as much as possible. Last but not least, we shouldn't forget about the fact that the equipment that is typically used in an R&D environment for testing a device is typically different than the equipment that is used in a production line environment. So we can't rely on the targets or the tolerances specified in R&D and then just copy paste them to a production line environment. We are not going to address this last topic during this webinar, but the rest of the topics I mentioned. So hopefully during the webinar, we'll present the ways of tackling many of these issues with different solutions from GRASS and Audio Precision. So the first solution I would like to present is the acoustic test chamber from GRASS called the AL30. It's basically a small acoustic test chamber that will isolate the test from the background noise that we have in our production line. But not only that, it also keeps the test noise inside the chamber so it doesn't disturb the environment and the operators around the test area. It has a drawer on the front that will allow us for quickly device under test exchange. It also has shock and vibration absorbing feet, and it's basically used for quick and reliable tests of mobile phones or tablets or loudspeakers such as speakerphones or smart speakers or any other similarly sized acoustic device. If you look at the bottom of the screen where we have this chart here, we are showing a graph with 10 consecutive measurements of the same DUT. And you can see that it's basically showing the same curve for all the measurements. And this is because the AL30 is providing the right environment so we can perform a repeatable and reliable testing of our devices. So if we look at the interior, of the AL30 over here, we can see that the AL30 has absorbing material, and this will optimize the environment so it has as little influence as possible from the test chamber. We can also see that we have a door on the back, and the door will allow us for easy setup of all the test equipment inside the box. And we can see some test equipment inside the box over here. We have mounting points where we can mount measurement microphones, like here on the bottom and on the top of the AL30. But we also have a mouth simulator that it can be used as a reference sound source. Then, as I mentioned before, on the front of the AL30, we have a drawer, and on the drawer we have rails, and these rails have rulers that can be used to recall the exact same positioning of your device on the test, so we can repeat the same testing in different production lines. We can see in this case we are testing a small tablet. So the AL30 comes in different versions. We have the standard AL30 and the AL30S2. All these different versions of the AL30 have the same outer dimensions and around the same weight. If we look at the standard AL30 and compare to the AL30S2 in the middle of the screen, we can see that the main difference is the size of the opening. The AL30S2 having a larger opening of the drawer. The AL30S2 comes in two different versions, one of them with a high drawer mounting and the other one with a low drawer mounting. The basic difference between all of them is the top clearance, and we can see that the AL30S2 with a low drawer mounting will allow for the testing of the bigger type of devices. Maybe you already seen this from the pictures before, but on the side of the AL30, we have a connector panel. And this connector panel will allow for the interface between the inside of the test chamber, where we have our device on the test, and the outside, where we have our data acquisition system or our analyzer. The connector panel can be custom configured in different ways, and we have a huge range of connectors going from BNC to RCA, XLR, and so on. If the connector you want to use is not here on this list, we can always leave a blank plate in the connector panel so you can mount the connector of choice afterwards. The AL30 will give you the chance of using 8 different custom connectors, while the AL30S2 has space for 10 connectors. As we have seen before, on the drawer, we have the rails where we can mount our device on the test. In order to mount the device on the test on the rails, we have device and the test holders, and we have different types of holders, as you see here on this slide. So the different holders will allow for the proper mounting of DUTs of different sizes and different shapes. We also have holders for measurement microphones, and the measurement microphones can be set up inside the chamber, like we see over here, a bottom mounting or a top mounting, or they can be set up directly on the rails of the drawer, like we see on the top right corner of this slide. We also have accessories to mount other testing equipment, such as a reference sound source, like the example over here. This is a mouth simulator that can be used as a reference sound source to test, for example, the performance of microphone of our mobile phone, for example. And here we have an example setup. or we are testing a small tablet, and we can see that we have measurement microphones both inside the test chamber, but also on the drawer. We're also using a mouth simulator as a reference sound source, and all the equipment is connected through the connector panel on the side of the box to interface with the analyzer outside the box. So once we are ready for testing, we have to close the AL30's drawer, and then we can start testing. As we can see on the right of the screen, we have the self-insertion loss of the AL30 that will protect our test from the background noise around the test environment. And up here, you can find links. You will be able to access this link via the PDF in the handouts section, where you can find more information about the AL30. So the next thing I would like to talk about is a brand new microphone from Grass. This is a microphone that has been designed specifically for production line environments, and it's called the EQ40PM EQset miniature production line microphone. This is a 1/4-inch microphone, as you see on the picture on the left, and it's just 34 millimeters long. If we look at the specifications of these microphones, we can see that it's optimized to work in the audible range from 20 hertz and up to 20 kilohertz. And you will also note that from 20 hertz and up to 10 kilohertz has extremely tight tolerances on the frequency response, just 0.5 dB. This is very unusual for a microphone designed for production line environments, which are cost-effective microphones. And then up to 20 kilohertz, we have plus minus 2 dB. The nominal sensitivity is 25 millivolt per Pascal. And you also note the unusually tight tolerances on these sensitivities, just plus minus 0.2 dB. The noise floor of the microphone is around 30 dBA, while the acoustic overload point is around 120 dB SPL, measured with 3% THD. We'll come back to environmental stability, but this microphone has a pretty good specification when it comes to environmental stability, better than 0.3 dB. I will come back to this later in another slide. This microphone is designed to be powered with a CCP interface. CCP is one of the most common microphone supply for test and measurement equipment. ICP, IEP, CCLD, these are just different names for compatible technologies. That means that if you have a data acquisition system or analyzer with this type of microphone supply, you will be able to connect this microphone directly to the supply. We are using an SMB connector, but the most important thing about this microphone is that it has the EQset technology. Let me come back to this in a split second. But first of all, let's look at the target of this microphone. This microphone is not designed to replace the standard measurement microphones, but instead it's targeted to replace the typical microphones that are found in a production line environments. These are usually called array microphones or QC, from quality control microphones. And some examples of this type of microphones are the ones here on the left. These are cost-effective microphones. And the new Grass 40PM will have the same dimensions. It has the same type of SMB connector, and it's powered in the exact same way as these very, very popular microphones that you find in many production lines around the world. So now let's talk about this EQset technology. This is a patent pending technology from Grass. And the concept here is that we would like to keep a 100% analog sensor, but with some built-in electronics that will allow for the correction of both the gain, that will be the sensitivity of the microphone, but also the frequency response curve. In order to do that, the microphone has a built-in equalizer. We are basically taking the acoustical signal and having an analog to digital converter. So we get a digital signal, and then we can change the signal or do signal conditioning the way we want to fix the gain or to have a completely flat frequency response. And after we finish with the processing, the signal will be converted into the analog domain, and then you get an analog signal on the output of the microphone. So all these electronics are inside this very small housing. We call it a transparent technology from the user's perspective, because it doesn't require any changes in your signal change or any input from the user. You can just use your existing interface, your existing data acquisition system. We are reducing the complexity of all your test setup, speeding up all the installation, as all the microphones, all the 40 PMs will have practically the same sensitivity and practically the same flat frequency response without the need of making any compensations at all. This Graz EQ 40 PM is the first microphone that we release with this EQset technology. So we are expecting in the future to have more units using this revolutionary technology. So I hope this next slide will help us understand why microphones using this game-changing EQset technology, like the Graz EQ 40 PM, are so much better than your standard production line microphone. So first, let's see what is a typical way of working with your classical microphone. Let's say you have a production line and you will get 100 different production line microphones to work in your production line. So out of the box, you will get something like this. All the microphones will have big deviations in the sensitivity. It can be up to ±2 or ±3 dB difference between all the different microphones. But not only that, the frequency response is far from being completely flat. So the typical way to work with this is that you will use a sound calibrator or a piston phone or the TETS chip to try to compensate for all the sensitivity differences. But we need to consider that these compensations are only happening at one reference point, that it could be at 250 hertz or 1 kilohertz. So the rest of the frequency response is still not flat. So something that you could do about this, and it's very rarely done, particularly in production line environments, it could be to compensate for this non flat frequency response. But this will take a long time, because every microphone has a slightly different frequency response. So you'll need to know this frequency response in order to be able to perform a compensation in the 100 units that you have. So let's compare that with a microphone like the EQ 40 PM from Graz with the EQset technology. So this is what you're going to get right out of the box. All the microphones will have practically the same sensitivity and practically the same flat frequency response from 20 hertz to 20 kilohertz. So we don't have to worry about any compensation. We don't have to use valuable time in calibrating each unit, and we don't have to use valuable time in compensating for the uneven flat frequency response. And this will save you valuable time in your production line. So what's the meaning of all this? Basically, that you will reduce your measurement uncertainty. Your measurement uncertainty is going to be much smaller. I know we have a lot of information here on this slide, but let's concentrate on the left part of the slide for a second. Um, and here we can see the tolerances in the frequency response for the typical QC array microphone, the typical microphone that is used in a production line environment nowadays. Some examples is the microphones we see here in the bottom left. These are great microphones, but they are relying on an older technology without the benefits of the EQ set. So the frequency response can be anywhere between this red area. Of course, as we said before, the sensitivity differences could be compensated using a piston phone or a sound calibrator or TEDs, but we are only relying in a single frequency point, and we still don't know what's happening on the rest of the frequency response. If we compare that to a microphone with the EQ set technology, like the Graz EQ 40 PM, we can see that the situation is very different, with a very tight tolerance in the sensitivity, only plus minus 0.2 dB, and a very tight tolerance in the whole frequency response. So that means that we can forget about TEDs. So we don't need to use a data acquisition system that is relying on the use of TEDs, because all the microphones from Graz, all the Graz EQ 40 PMs are practically the same. We don't have to compensate for difference between each unit at all. So we can forget about TEDs and we can rely on the use of more cost-effective data acquisition system or sound cards. The Graz 40 PM makes a great match with analyzers like our Audio Precision APX 517 that we see up here, which is optimized for acoustic measurements in a production line environment. But it will also make a good match with an inexpensive audio interface like the one we see down here, that can be combined with Audio Precision's APX Flex interface to be able to use Audio Precision software with third-party hardware. But then from my previous slide, you might ask yourself how come you can use 40 PM directly with an inexpensive audio interface, when I mentioned in the beginning that 40 PM has to be powered with a CCP supply. Well, the thing is that we can also use the 40 PM with plus 48 volt phantom power. We just need an XLR to BNC adapter. One example of that is the Graz AG3, and then we will be able to connect the Graz EQ 40 PM to inexpensive audio cards with plus 48 volt phantom power, and then we'll be ready to go. So in some cases, people might rely on TEDs for identifying the sensor, but as I mentioned before, TEDs is really not necessary here, as all the microphones are exactly the same, and you actually don't need any compensation for sensitivity differences or frequency response differences. But just in case, we have the serial number of the side of the microphone, and we also have a barcode, so you can use a barcode reader to identify your sensor if you still want to do that. Another important thing to consider is that we design the Graz EQ 40 PM to be very easy to produce and very easy to scale. So it doesn't matter if you need one sensor or if you need 100, we'll be able to deliver this microphone really fast. I talk about environmental stability, and this is a very important topic when it comes to production line microphones, because we might have production lines in different points of the world where the environmental conditions are very different. In the case of atmospheric pressure or temperature or humidity, the good thing is that you can forget about compensating your microphone for different atmospheric pressures or different temperatures at least when it comes to the typical environmental conditions that you find in typical production lines around the world. And here we have an example of a comparison of the new Graz EQ40PM against a typical production line microphone when it comes to temperature changes. We're going from 10 degrees to 45 degrees Celsius and then back to 10 degrees Celsius. And we are seeing how the sensitivity of the microphone changes over time. We can see that a typical production line microphone, we have a big deviation in the sensitivity because of the change in temperature, while the 40 PM stays fairly flat. So this is something to consider in order to increase the reliability of your test, and forget about the differences in sensitivity or frequency response that that a production line microphone can have due to environmental changes. You won't have that type of issue with a Graz EQ40 PM. So as a summary, we can say that we have a very price competitive microphone. We are not talking prices in this webinar, but you can contact your sales representative and you will see that the microphone is priced in a very competitive way. The microphone is very stable, even when you change the temperature, humidity, and static pressure. We're talking in the typical environmental conditions that you will find in different production lines around the world. It's very easy to set up. It's a plug and play setup, backwards compatible with your typical production line microphone. It's very easy to replace because every 40 PM is exactly the same. You don't have to compensate because of sensitivity differences or frequency response differences. And it also allows for the use of entry-level audio interface with no TEDs or no CCP supply. You can just rely in your inexpensive audio interface with plus 48-volt phantom powers if you would like to. And all this will minimize your measurement errors because of the very flat frequency response, or the fact that we don't have any differences between microphones in the sensitivity. We have a fixed sensitivity. We can deliver this microphone with a short delivery time, even in high quantities. We have the barcode for easy identification. And basically all the things I'm mentioning will help you cutting costs and cutting the downtime due to calibration or due to changes or problems with the reliability of your typical production line microphone. Here we have a very interesting link with an online calculator where you can calculate how much is your microphone calibration costing you, how much time you're using for calibrating your production line microphones, and how is that affecting your bottom line. On the top here, we have some links where you can access more information about the Graz EQ40 PM microphone, and also some extra information about the EQset technology. And with that, I'll finish my part of the presentation, and I'm gonna ask my colleague, James Kelly from the UK, to join this webinar. Thank you very much.
Thanks, Santiago. I'll just share my screen. So hopefully you can all see my image of the APX 517. And there's a link here for you to get more information on the 517. It's an integrated system for production test of headphones, headsets, speakers, and microphones. It has a built-in power amplifier, an analyzer, also has a headphone amplifier, which can be configured with user interchangeable plates. So from a 6.3 millimeter TRS jack, or a 3.5 millimeter TRS, or 2 BNCs on the headphone output. which is just here. And it also has 4 inputs, usable 2 at a time and in any combination. So you could have a single channel CCP microphone, and the other channel could be 48 volt phantom if required. It also has a slot for one of our optional digital I/O modules. And this makes the 517 very flexible and also very popular when testing things like Bluetooth speakers, smart speakers, Bluetooth headsets, etc. Another very common interface for production test is the APX 500 Flex. And the APX 500 Flex is delivered as a USB dongle. It allows you access to the APX 500 software using the ASIO interface to connect to any ASIO compliant sound device, typically USB sound cards or even PCI sound cards that you might actually install in a PC. Again, there's a link on this page for more information on the APX 500 Flex. And we're now going to have a look at this setup specifically and how you'd go about using a USB device with APX 500 Flex with the AL30 and the 40PM EQ set microphone. So, as Santiago mentioned, a cheap alternative to an APX analyzer. What I'll be using today is an RME Fireface product with APX 500 Flex. Some things you need to note about configuration. This is one of our supported devices, so there'll be pre-furnished project files and templates with analog ratios already programmed for this device. So you get them with the APX 500 software. You can just choose that from a template. So with the RME Fireface, you get this Total Mix FX software. And the reason I need to discuss this is because you use this to, for example, turn on 48 volt phantom power in the system. And this you can only do from this interface. And you can launch this from within APX, and you can change things directly in APX, such as sample rate. But this you need to actually do from the RME Total Mix FX software. There you can see it's this is expanded by clicking on the little spanner icon for the additional tools, and it brings up these settings. So when using the 40PM, the great thing is we don't have to do a calibration. all 40PM microphones have a sensitivity of 25 millivolts per Pascal, and you simply need to have that set as your sensitivity in your APX project file. You can see here, actually, you can see the scaling factor for our ASIO interface for the RME. And then once we add our sensitivity for the microphone, we'll be getting accurate dBSPL measurements. So how does that differ from something that doesn't have EQ set? As Santiago mentioned, you'd need extra steps and in most cases an extra sequence in your project file to calibrate the mics. And this would typically be done at the start of a shift. So it would be repeated as and when required, as and when even you get environmental changes. And I have some personal experience of that working in China. For acoustic measurements, we typically run through a calibration sequence at the start of every shift because temperature and humidity change so much from day to evening and then through the night. So here you might see our different sensitivities set for our different microphones we're using. These will be the same model of microphone, but with different sensitivities. And all of this takes time, obviously, which costs money. And this is downtime for your production line. Obviously, the other case for running calibration is if you need to replace a microphone. And again, this is where the 40PM really does come into its own, because you can just change the microphone without making any changes to the project file. And there you can see that difference in sensitivity between two of the same model of microphone. So here I'm going to talk a little bit about an open loop continuous sweep and our audio file settings. It's important to realize that when you're generating a file to be played back, that the sample rate matches the sample rate of the device that's acquiring the signal, so that the APX software will get the correct data from the device. So luckily the RME Fireface will run at 192 kilohertz. So we can generate a WAV file at 192 kilohertz, 24-bit. Number of channels. So you configure the sample rate and the channels. You then configure your pilot tone frequency and your start and stop frequency for the sweep. And then the levels for the pilot tone and the levels for the sweep. And any EQ if required. But since we're actually trying to measure the response of the speakers from the tablet, we don't want any EQ. And then you've got configuration for durations of the pilot tone and durations of the sweep time. And then lastly, some triggering, which you don't really need to do before you generate your signal, but you do need to adjust this dependent on your acquired data level. So you will just typically just adjust the level threshold based on your pilot tone level when you acquire it from the loudspeaker. And once you've done, you generate this, it will create a WAV file, and then you transfer this to your device under test. Typically in a production environment, this will be preloaded and possibly even in some form of test mode on the device under test, which will play repeatedly on the when it's ready for production line testing. Another test you could use, which I'm not using today, is a multi-tone, and very similarly, you can create your own multi-tones by viewing the signal definition, the sample rate, and then creating a WAV file again for transfer to the tablet. You can create your own multi-tones, and this might be a good idea if, let's say, you want to make sure you don't include a tone that's the same frequency as your pilot tone for your continuous sweep or for your log chirp, so that you don't get inadvertent triggers. And again, here you can see you've got controls for sample rate, the length, and the frequencies. So totally customizable, and then you can create the WAV file. So ease of setup and configuration, reduce the time spent on calibration and reconfiguration, reliability and repeatability to ensure maximum uptime, and affordability. So really the APX 500 Flex is our most affordable option for running APX 500 project files. So typical devices under test: headphones and headsets, speakers, microphones, or devices with speakers and microphones within them. And this is basically whether you're using Flex or the APX 517. So APX 500 measurement software has a versatile, powerful and fast interface, has one-click measurements and automated reports. It has a inbuilt sequencer for code-free automation, which you'll see on the top left of the screen, and also has a full API if you want to create your own programs in VB.NET, C#, MATLAB, or LabVIEW, etc. Common software platform, so there is only ever a release of APX 500 software. Obviously, we've released different versions over the years, but that one version of software runs on every single APX analyzer and APX 500 Flex. Production test mode and project locking makes it very simple to secure a project for distribution to a production line. So just a little bit about our support centers around the world. We have technical support here in the UK, in Denmark, in the US, and also in China. And we have service centers also around the world, offering repair and calibration of both AP and GRASS products. So as we're running short on time, I'm going to run a quick demonstration, and the products I'm using here, I'm actually testing a tablet. I have two 40PM microphones connected via two XLR to BNC adapters to my RME Fireface channels 1 and 2 mic inputs with 48 volt phantom power turned on, all through the patch panel on the GRASS AL30, and then the tablet will sit in the drawer. I'm running APX 500 Flex, and I've created a project file to run this. So I'm just going to switch screens. So here you can see the project file. And you can see I've actually got two sequences here. I don't need this sequence for when I'm using the 40 PM, but I thought I would leave that in just to confirm that if we did want to use other microphones, we'd need to run a separate sequence, calibrate the mics before we could run the measurements. But I'm not going to show that. What I'm going to do is actually just run this tablet test, and I'm going to enter a made up serial number, and then I'm going to follow these prompts. So as I said, in a production environment, this might be controlled via a test mode. It might be via the USB interface. You might be able to control this and play a specific test track. But for my purposes, I'm just going to play a track on repeat, close the drawer, and there you can see our test has passed. So it's if I unlock this, I can show you how this works. You can see I've been doing a number of units this morning. I have an average runtime of 15 seconds, pass count of 18 units, and a perfect first time pass yield. And I do actually have some limits on some of these results. So very quickly, I'll show you how this project is configured. So we have our sequences, and you can choose on different actions depending whether the sequence passes or fails. And again, you could have, for instance, you might want a password required if you did have to calibrate mics, because you might not want a production operative to run the calibration. In the sequencer properties, this is where you choose your image as the banner image, where you then select which sequence you want to run. And then in my prompt, where I enter the text instructing the user. So I'm just going to stop this playing. And you can preview this, and the image is you just browse for the image here. So, and then that you can preview that. So then the only measurement I have here is continuous sweep. I've got an RMS level. I've then smoothed that, and I've applied limits around the usable part of really the loudspeaker response. There's really not much going on below 200 Hertz, so I've only set limits around 200 Hertz. And I've created this with an offset so that from 1K to approximately 10K, it's plus or minus 2 dB, and then it's plus or minus 5 dB at the extremities. I've also added a derived result to get a RMS level at 1 kilohertz. So this, I wanted to point out, is a possibility. Rather than doing something like play a 1 kilohertz sine wave, and use the level and gain measurement to get a RMS level at 1 kilohertz, you can actually get that from your sweep data. I've done a similar thing here with THD plus noise ratio. I've just added a derived result, and how you do this is just a right click on one of your other graphs, add a derived result, and I've chosen specify data points and a single value, and it will default to 1 kilohertz, but that could be any value. So in your derived result settings here, it will tell you which data it's working on, for example. And here's your frequency. So I could change that frequency and get THD and others. And you can have multiple derived results. You can see our acquired waveform, our pilot tone, and our chirp. And also we get a very, very nice impulse response. And as I say, no calibration required in our signal path setup. Our predefined template has our scaling factor in for the RME fireface, and then our sensitivity is always 25 millivolts per Pascal for the 40 PM. And it's as simple as that. It just makes acoustic measurement on a production line so much easier than using traditional measurement microphones. So with that, I'd like to thank you all for attending, and we'll have a look if there's any unanswered questions. Okay, we've got one question here saying, what options are available for integrating the shown production test sequence into other software? Is there a driver DLL API available? Yes, the API is a full API into the software. There's examples for C#, C++, VB.NET, and the examples all work on the basis that you create a sequence in the APX 500 UI, and then either call individual measurements or run the sequence from that environment and call it via the API, and then either extract data or just save a report as we are in the user interface. So yes, there is a DLL which has all the API calls embedded, and we support, as I said, all of the .NET base languages and also LabVIEW, but also Python with the PythonNet module. And there's another question here, how is your FS factor chosen? So if you're talking about our scaling factor, so 380 milli-FS per volt, this is actually chosen based on the sound card you're using. These are, we have a number of, if I look at the project templates, we have a number of Flex pre-configured templates, which includes scaling factors for the Lynx Aurora, Lynx E22, and 2 of the RME Fireface products. So they're already pre-furnished templates with those scaling factors in from comprehensive measurements done on those devices. There's also a link on our website on how to evaluate a USB sound device for use with APX 500 Flex, which you can use another form of measurement to basically define these scaling factors for your sound card, and then you can use any ASIO interface with APX 500 Flex. You don't just have to use our supported devices, but these are our pre-furnished templates that you get with APX 500 software. So hopefully that answers those 2 questions. So there's a question here, how about noise levels of the interfaces? Is there some numbers to this? Well, considering certainly in this application, considering all of those devices are 192 kilohertz 24-bit ASIO devices, they will have different front ends, which some will be noisier than others, but certainly the ones we support, we have chosen for their quality. But you would be able to measure this via the ASIO interface and quantify it. So yes, some devices are going to be better than others. Obviously, this is promoted as a production line low cost solution. If you want better quality, lower noise, then choose an APX analyzer. But obviously that then increase your cost. But these devices that we support, I can say, are actually very, very good. And where they fall over really is their limitations on things like maximum input levels, whereas our APX analyzers can measure both very, very low levels and usually in the ranges of more than 100 volts or maybe even 200 volts. So any of these ASIO sound cards are not capable of that sort of range of measurement, but their noise floor of our supported products are very, very good, and you can get a full list of supported products from the AP website, and there are links on the handout for all of that information. Yes, it is certainly possible to use Pro Audio interfaces, and actually many of our customers are actually the manufacturers of those types of devices. So yeah, Focusrite, RME, all of those Pro Audio manufacturers are using APX 500 software. So if there's no more questions, I think we can end the webinar there. unless Santiago, do you have anything else to add?
Well, if you have more questions, you're always welcome to contact us via email at support@grassacoustics.com and tech support@ap.com. And of course, remember that you will get a copy of the recording of this webinar. And also don't forget to download the handout where you have the PDF, the copy of the slides in the dashboard of this GoToWebinar platform. So I guess now that we don't have any questions left, we can say thank you very much for attending and see you in the next webinar.